first let me take a pledge. So I watched my videos. So yeah, I before I took a pledge about that I have to make sure that I will not stammer, but what I have saw that I was trying to use the energy and I am using the body movements uh, to I am forcing to the sound to come from the mouth and it is wrong. I have to speak with very minimum energy, like एकदम मतलब minimum sweet type of energy. So today I my focus is not only to make sure that I will not stammer. I will also have to make sure that I am still my body head movements is relaxed. Okay, so start. So today I have our notes. So I was reading the notes. So I decided to read and make you understand the notes. This is a chapter from the course named High Speed Aerodynamics in our fifth semester. Okay, so the topic name is one dimensional gas dynamics. Okay, I am trying to explain you with vocal as much as I can, and I will make sure that where it is hard to explain with vocal, then I will write or draw something. So let me start. Okay. So we start from the one dimensional flows governing equations. So we have three governing equations. First is the continuity equation. So d rho mu equal to 0. Here we are considering that the flow is is constant. Okay, and the momentum equation is dh plus momentum equation is dp plus rho mu d mu equal to 0, and the energy equation is dh plus d mu square by 2 is equal to 0. So this is the simple governing question. Now one thing is the important, if you want to know that from where this continuity equation comes, so if we consider a channel like this and take two part rho 1 mu 1 rho 2 if we also keep the area here A1 A2, so here the so we write that del by del t of rho a delta x means this is the length delta x. So rho a is the amount of mass here in this region is changing, is only and only due to the mass flow rate from here and from here. We have to check. So equal to minus del by del x rho mu a delta x. Okay. So how this comes, we have to write this in the form of like this. Go to plus we are considering now. I forgot that how to write this. It is in my laptop. I will show you next time that how it is coming. I will show you. Okay. So this is the equation. Same we can write using 2 plus 14. Okay, again let's forget about this. This is not so important, not so hard. Okay, let me erase this part so that we can focus more on solving problems. Okay. So we have the other equation cos 30 cos 0, the direction from total derivative momentum equations. We have here in my notes I have the questions from where the governing equations came. So I will also write here, but that's time of waste of time for me. What I'm trying to slow down with the concentration. Let me go into the important part. Not hard part. Yeah. So we are considering we are now looking into the shock wave. That's important. And motion of the disturbances related to the fluid is called wave motion. Okay, and the speed of propagation is called wave speed. Let's see that what I'm saying that if the fluid is stationary and its shock is moving with respect to speed v1 equal to cs. The gas is stationary, and what happened when we look from the source point of view, the flow is coming here with speed v1 and moving out with speed v2. There is some changes, so if we assume q2, so if we again come back here, so v1 in the other is, so this one is cancel out, so this will come as v1 minus the static pressure and temperature. We will assume we will static pressure temperature do not depend on the frame of reference, but the stagnation pressure and temperature depend on the frame of reference. So this we have to consider. So okay, so we can write here, let's write mu p. So mu p is equal to mu1 minus mu2, and we can write this as like shock is moving at speed cs. There is a piston, okay, a piston which is moving with speed mu p, and here is some pressure to it. May be assumed that the fluid behind the shock wave is followed by the driving piston moving at the same speed mu p. Okay, so what I'm thinking that I'm not able to follow this. I have to stop. I have to stick with. Okay, so here I will try. So yeah, it is the reason of the compressed fluid between the shock wave and the piston increase in the length of cs minus mu p, as you can see easily. Okay, then what? Then these figures equations will include maybe the but okay. So from here we can find the equations of cs, rho 2, p1, p2 using the shock wave relations. Okay, so my concern is that we if the proper the proper heating shock wave poses a general problem given the form of the disturbance at some time t. How does it change subsequently, and what are the relations between the various quantities involved? Means अगर if we have the shock wave, if we have the disturbance in at some time t, so we want to see that how it changes. Okay, so the problem is, so we are considering two uh, yes, we are considering two situations where the flow is unsteady and it is non-stationary, adiabatic and non-viscous. Okay, all the constraints. So the continuity equation from the first that I showed you comes like this, that del by del x plus mu del p by del x equal to 0. This is the continuity equation, and del mu by del p plus mu del mu by del x plus 1 by mu del like del del 2 so del 2 by del x equal to 0. This is the continuity equation. This is the mountain equation. We can write this. We are what we are taking here. We are taking rho is equal to rho 1 plus x s dash, where rho 1 is the constant. Okay, so you have got a disturbances and or permutations are defined relative to the portion of the fluid that is at rest with mu is equal to 0 and rho is equal to 1. Values of mu different from zeros and values of rho different from rho 1 are called perturbations. Okay, so yeah, we change this in, we can substitute this in both of the equations. So what we get, we can get so, and okay, after substituting these equations, these equations are exact for frictionless non-conducting motion, but not easily integrable as they are non-linear. The equations can be linearized, and a considerable simplification realized by making small disturbances assumptions. So we are taking as dash is less than equal to 1, so we can neglect as del mu by del x and mu del x by del x. We are ignoring these two terms. So after ignoring these terms, what we get the linearized solution, the linearized solution as del s by del t plus del mu by del x equal to 0 and del mu by del p plus a1 square del s by del x equal to 0, where and this and this we can also write, and this is the dimensional this quantity, so rho minus rho 1 by, okay, so this is the, you can take dimension is quantity, so these are called what we can say, these are called acrostic equation. Actions why because we are taking as less as very small as compared to the one, so the changes is very small, so we can write it as a acoustic equations. So okay, the corresponding approximations in the isotopy for a perfect gas scheme. Okay, this is okay. So what we are doing, we are differentiating the linearized continuity and the Mendel equation with respect to t and x, and after solving these two equations we can get s plus and t square minus a1 square then s plus divided by x square equals 0, or you can write as just both the disturbances you use this equation. This is the as and one more discussion which similarly is defined as del 2 mu by del t square minus a1 square del 2 by del x square equals 0. Okay, so this is the two wave equation. You can see that you can write as tt minus a1 square x plus x equals 0. This is the wave equation after solving, after differentiating the linearized continuity and the Mendel equation with respect to x. Okay, so the general solution we get is s plus equal to x minus a1t plus t x plus a1t and mu is equal to minus a1t plus this is the general solution of this. After solving this solution of this, the general solution of this is this. The changes we talk with here it is minus a1 square, here also it is minus a1 square. So okay. So to analyze the characters of the solution, let's take z equal to 0. If we take z equal to 0, so as this is coming as f x minus a1t. Okay, so this represent disturbance or wave which at t is equal to 0 had the shape. Okay, t is equal to 0 है तो ये होगा, this represent a disturbance or wave which at t equal to 0 has shape as is equal to fx. Okay, and which at time t has exactly the same shape but with corresponding points displayed the right, and that is the velocity of each point in the wave, and the wave itself is given. Means what we are saying that the wave is propagating with each of the particles is moving with speed given. So we can write it. So nice. So the wave as this is it only one direction is called is a simple wave. Means we are calling this a simple wave. Similarly, the wave described by h dash equal to g is, if we take f equal to 0, is a simple wave propagating to the left with speed a1. Means here it is negative, so it is going here. Here it is positive, so the wave direction is negative, but the velocity is same. Let it e, the speed of the wave. Okay. So the lines that's xt plane which traces the progress of the waves, that is the lines with slope ds by dt is equal to plus minus even are called the characteristics of the wave equation. Okay, simple. So simple that. So the speed of sound, we can write the speed of sound as like this. Have speed of sound, so you first know that a square is equal to del p by del rho at constant entropy. Okay. But del p by del x, so it's del p by del x equal to a square del rho by del x and but when the flow is non-isotropic, so we can write as del p by del x equal to a square del rho by del x. So we have to consider that del p by del x changing with entropy, considering that the molar density is constant and therefore by the x. It is quite good. Okay. So pressure and particle velocity in sound wave. Okay, let me read the pressure disturbance accompanying the density wave or a coupled gas means what we have seen the density disturbance as Sx. So we can write pressure disturbance in the form of P1 P by P1 is equal to 1 plus gamma as this. This is the density disturbance where the pressure wave has the same shape as the density wave, but differ by a constant factor gamma. So as the wave progress, so the fluid, the pressure, the disturbances sets the fluid in motion, giving it velocity mu, which is called the particle velocity, which is in general is much smaller than the wave speed. Even the corresponding velocities in the shock problem are mu p and cs. Okay. So a simple way of addressing distance is equal to a1 the fact that the wave produces on the fluid depends on the gradient of density and the pressure distribution and on the direction of the motion of the wave, the portion of the wave that increases the density is called compression. That's a simple thing. There's nothing about that. So let's start with the most important topic: linearized shock wave. The next topic we have is a diaphragm. Here it is high pressure. Here it is. So okay. So let's consider that we have the low pressure here and we have the high pressure here. Okay. So let me read this for you, that shock tube are simply a tube that is divided by a membrane or a diaphragm into two chambers in which pressures are different. When the diaphragm is suddenly removed or broken, a wave motion is accepted if the pressure difference is so small then that the motion may be approximately described by the acoustic equations. The shock tube is called acoustic or linearized. We have shock tube. I want to see that many concept here, which is we can give them. Okay, then let's go one by one. Let's not jump directly into the real shock tube, means where the shock wave and the expansion wave is moving. We will go there, okay, for sure. So let's see what he is saying that, okay, at t is equal to 0, immediately after the membrane is removed, the wave has a shape of step distribution, okay, because here is the high, here it is a high pressure, here it is low pressure, so there is a sudden jump in pressure, so we can write it as a step function, means there is a sudden changes in the pressure. So the wave has a shape of step distribution. हम लोग when we remove this membrane or diaphragm, immediate at t is equal to 0, the wave have the step function. Okay, so the particle velocity at this instant is 0 everywhere. The wave at t is equal to 0 is the particle का जो ये है velocity वो अभी 0 है at t is equal to 0, so we can write x dash x0 is at t is equal to 0, fx plus dx. Okay, we can write it as s naught x density, and x, when x is greater than 0 it is s4, and when x is less than 0 this is 0, okay. And mu is speed we are taking as like a1 fx minus a1 gx. I can show you that here the equations is coming is like that. There it is. Here it is plus, here it is also plus, but f is equal to a1f and g is equal to minus a1 g, so here it is negative, so it is cancelled out and coming as 0. Okay, and t is equal to 0, both is same. You share and write this also. I write this in the, you write in your fx minus a1t plus gx plus a1t mu is equal to x minus a1t plus g plus a1t. So this is the two equations. Step function, okay, mu x0. So here at d is equal to 0. Here one thing you can write f is equal to a1f, f is equal to a1 capital F and d is equal to a1 capital G. So when d is equal to 0, if you substitute this, you can get 0. And simultaneous solution, give fx, here it is give fx equal to cx equal to half x naught x. Okay. Hence the description of the motion at any subsequent time is, here it is writing like as does xt at any time t is half x naught x minus a1 t plus half x naught as x plus a1 t. You can write it here when x is greater than a1 t, when x is greater than a1 t, so coming as 4 S4 minus x okay. So okay, let me also see that how it is coming. So we have x equal to 0 at any time t can okay, understand. So if you have we have xt, right? Okay, so x naught so from here it is coming from here, that's not here that हमारा x naught is so fx की जगह हमारा तो हमने fx की जगह उसका क्या रख दिया, ये रख दिया, और इसमें b की जगह क्या रख दिया, ये रख दिया. ठीक है, कुछ नहीं किया. अब अगर हम लोग इसको देखते हैं x ग्रेटर देन, ये जो है हमारा क्या है कि अगर x हमारा ये है ग्रेटर देन 0 है तो s पर होगा, मतलब कि ये अगर तुम्हारा x minus a1 t greater than 0 है, सो इसका वैल्यू greater than 0 है तो इसका वैल्यू कितना हो जाएगा, तो तुम्हारा x तो ये हो जाएगा तुम्हारा x4 ओके. इसका वैल्यू greater than 0 तो x से बड़ा है, उसका भी मतलब अगर ये है तो दोनों ये है पॉजिटिव है तो हाफ s4 प्लस हाफ s4 प्लस 4. अगर तुम्हारा ये है पॉजिटिव है, एक अगर तुम्हारा नेगेटिव है तो एक हो जाएगा 0 तो भी है हाफ s4, एंड अगर दोनों अगर नेगेटिव होता है तो हो जाएगा 0. सो सेम विथ xt, same we can write with qst, and I'm not going to write the equations. So okay, so at t is equal to t1, here it is x, here at t1 at any time t, the t is going like this. So जैसे ही मैंने इसको छोड़ा, अच्छा यहाँ पे एक हो जाएगा इक्वल टू 0, हाफ s4, एक हो जाएगा तुम्हारा, दिस इज लाइक दिस, 0 0 half s4 s4 0 half s4 s4. This is the division 1, this is division 2, this is division 3. Okay, you can write 4. Okay, and the base is चला था हमने जब इसका इक्वेशन देखा था तो ये है इस साइड है हमारा वो भी कंप्रेशन वेव है, ये तुम्हारा एक्सपेंशन वेव है और तुम्हारा क्या है कंप्रेशन वेव है. So compression wave is propagated to low pressure side and an expansion wave of equal strength to high pressure side. Finite amplitude asymptotic waves. Let me close these from now. The next part we have to discuss the finite amplitude asymptotic waves and propagation of finite waves, centered expansion wave, and the last topic where is my shock wave, shock tube, non-linear solution. So we will also see this shock tube non-linear solution. This is interesting. I will try to make video as much as I can. Next video is on the next topics.